All right. So, so far, all of our derivations have used the method of direct proof. We've been working on doing proofs where from the premises that we're given, we find some conclusion that is entailed by those premises. Now, we have two additional methods that can be used to simplify long and difficult proofs that um, sort of shortcuts things. So the first one we're going to talk about is a conditional proof. And conditional proof is a derivation method useful for deriving conditional conclusions, but it's also useful for deriving other conclusions or just parts of proofs that we need. But the most obvious case in where we can use it is when the conclusion that we're looking to show is itself a conditional statement. For example, if P, then Q. So it proceeds by assuming the antecedent of a desired conditional and subsequently deriving the consequent. So the way this works is that a conditional statement, like if P then Q, is just giving us a hypothetical situation. If it happened to be true that there were P, then it would be true that there would be Q. So when we do a conditional proof, um, we're just taking something and assuming it. We're inserting it into our proof as an assumed premise, and we see what follows from it. And when we see what follows from that assumption, now we don't take our assumption as being true. It's just an assumption. But if something, for example, P follows from our premises after we assume, or sorry, if something Q follows from our premises after we assume P, then that tells us that if there were a P, and we don't know if there is or not, but if there were a P, then we could get a Q, and then we could say if P then Q is true. So let's talk about the method. So a conditional proof is going to be a subproof in your overall proof. So when you start a conditional proof, you're going to want to indent, and this is going to be really important to make really clear. So indent, and the first line of your conditional proof is whatever it is you want to assume. So in this case, we have an argument with the first premise being if S then P. The second premise is if P then Q. And the conclusion that we want to show is if S then P and Q. Now, because our conclusion is a conditional, we're just looking at the relationship between S and P and Q. If there were an S, and we're not given an S, but if there were an S, would it be true that P and Q? So when we start our conditional proof on line 3, we're going to indent like this to show that we're doing a subproof here. And everything, when you're doing a subproof, you can use all of the premises that come before it, including the ones outside of the subproof. But after you discharge the result that you're trying to find in your subproof, then you go back to not being indented, and you can't reference anything inside the subproof. The subproof is going to be sort of its own self-contained thing after you're finished with it. All right, so the first thing we're going to do is, and if some of this is difficult to follow, it might be helpful to maybe just watch the first of the homework solutions videos where I go through one of these and show you how I would work with a conditional proof. But we'll work through this example in the PowerPoint as well. So when we start a conditional proof, we're going to indent the line. We're going to take something that we're assuming. In this case, we're assuming S. And the justification for that assumption, we're going to write down as ACP, or Assumption for Conditional Proof. This is making it clear that we're not given an S, we're assuming an S, and we're going to see what follows if there were, in fact, an S. Now, like I said, we can use all of the previous premises to then see what follows. We inside the subproof here, we can treat premises 1, 2, and 3 as if they were all premises to work with, but we have to stay inside the subproof when we're using both of them together. So if we assume S, well, from premise 1, we can see that if there were an S, there would be a P. So we can go ahead and get P from lines 1 and 3 using modus ponens. And if there were a P, which we were able to get from our initial assumption S by using modus ponens on line 1 and 3. We can see that on line 2, we could get a Q. So with lines 2 and 4, we get Q using modus ponens. Now, since we have both P and Q, we'll have to put these on a line together. So we have P and Q, and our justification is lines 4 and 5 conjunction. We have P by itself and we have Q by itself, so of course we have P and Q together. Both of them are given. So we can see from this that starting with our assumption of S, we were able to get to P and Q using the premises that we were already given. So we'll go ahead and discharge our conditional proof here. Very important to pay attention to how to do this. So when you discharge a conditional proof, the result that you're going to get here on line 7 is going to be a conditional statement. The antecedent of that conditional statement is the first line of the conditional proof. It's whatever we assumed. And the consequent of the conditional statement is going to be the last line. Presumably, we're working towards getting the consequent that we're looking for when we're doing our conditional proof. And so we're trying to show that if there were an S, then there would be a P and a Q, given the premises that we have to work with. So here we discharge if S, then P and Q. And you'll notice that this is outside of the indentation. We've gone back to our regular non-indented format. We're outside of the conditional proof. And the justification that we're giving from this for arriving at line 7 is lines 3 through 6 conditional proof. Conditional proofs and indirect proofs are going to take usually more than a couple of lines. So instead of listing out all of the lines, you'll just say 3 through whatever. So our justification is 3 through 6 in this case. Those were all the lines that we did our subproof in. And we're done. Okay, so every indented sequence must be discharged before the end of the proof. You can't just leave, you can't stay inside a subproof and end your proof that way. The subproofs are kind of their own little worlds, and they work with all of the premises that are outside of subproofs that come before them. But any conclusions that we get inside a subproof aren't good by themselves. In this case, when we're doing a conditional proof, they tell us something about a relation. So here we have our first premise, if Q, then P. And then our second premise, if P, then not Q. And we're trying to show not Q. Someone might want to say, well, I can assume P. And then if I assume P, then I get not Q, and then I'm done. So it doesn't work that way. When you assume P, we're not actually given a P. We don't know if there is a P. And it's true that we can get to not Q from there being a P, but the only thing that this tells us is that if there were a P, then there would be a not Q. Hypothetical situation. The conditional proof only gives us a conditional relation of if something, then something else. And in this case, if P, then not Q is already given as the second premise, so we're not doing anything here. This would be a completely incorrect answer on an exam if you tried to show not Q this way. So an indented sequence is here in our proof system is a series of lines in a derivation that do not follow from the premises directly, but only with some assumption indicated on the first line of the sequence. So that's why it's important we start a conditional proof, we indent it to be very clear that this is not part of the normal proof. This is just something that we're assuming, and we're going to see if a certain relation holds or doesn't hold from that assumption. So within an indented sequence, you can use any formula in which that sequence is embedded, and formulas derived within an indented sequence can be used only within the scope of that sequence. So all of these things that we're doing inside a subproof only apply to that subproof. At the end of the subproof, we can discharge something, and then that we can use elsewhere. But the stuff that's going on inside the subproof stays inside the subproof. So after you discharge an assumption, you may not use the formulas derived within the scope of that assumption later in the proof. Those stay in the subproof. The only thing that we can continue to use in this case would be premises 1 and 2, and 6 and 7. After we've here discharged our if S then Q that we got from doing a conditional proof, we can go ahead and use lines 1 and 2 and 6 and 7, but since that subproof's done, we've discharged it, lines 3, 4, and 5 can no longer be used. If we didn't want to discharge just then, we could keep our subproof could be going longer, but we can't stop with our subproof unless we finish it. There's one exception to that, which is that we can start another subproof within that subproof, and then in that case, the rules apply. Again, you have to finish that subproof before going back to the first one. But so you can't ever go back to the main proof from a subproof without finishing it first, but you can start newer nested subproofs. Okay, so a nested sequence is an indented sequence within another indented sequence. So it is an assumption within an assumption. Assumptions may be further embedded in other assumptions, and definitely we can do as many subproofs as we want inside of other subproofs, but we have to work with whatever the most recent subproof was. We have to go there backwards. We have to finish that and discharge whatever our assumption is, and then move on to the next one. All right. So here's another example of a situation where things get all messed up. If we start with our first premise, if S then P then Q, and our second premise is if P then Q, and we want to show if S then Q. So we'll start our conditional proof by assuming S, and we'll see if we can find Q within it. And if we can find Q, then we can discharge. But as you can see here on line 3, we assumed S. On line 4, we got if P then Q from premise 1 and premise 3, modus ponens. And then we started an additional subproof here where we assume P, and this is the same sort of mistake that was made earlier. You can assume P, and if you assume P, yeah, then you get a Q. But we don't get if S then Q. We would have to discharge this subproof, which would give us, in the red numbered line here, the statement if P then Q, which we already had, but it doesn't help with anything. So we have to stay within whatever the newest subproof that we're working with and discharge that, and whatever we discharge from a conditional proof is only going to be in the form of a conditional statement. Now you can use this, of course, to with things like material implication to get other results after you finish doing that, but whatever you discharge from a conditional proof directly will be a conditional statement. We can't just get Q from it, for example. We have to get if something, then something else, because we're assuming something and we're seeing what follows from that assumption. Okay, so that's a sort of real quick and dirty example of what conditional proofs are. I think it would be it's sort of difficult to explain because it's really simple. And it's straightforward. It's just a rule that we can follow. But it does. There's a lot of situations like this where people think, well, I can just assume something, and well, after you assume something, well, it turns out that you can get to whatever conclusion it is that you want to show within that subproof, and then they think they're done. But that's not how it works. In the subproof, you always have to discharge it in a certain form. In a conditional, you discharge it as a conditional statement, where the antecedent is the first line of the conditional proof, and the consequent is the last line of that conditional proof. We don't just get Q or P or something out of it. So you have to be careful about what it is that a conditional proof is doing. So this is what I would stress the most, and I think this is also very helpful to keep in mind if you're trying to wrap your head around what's going on with a conditional proof. We're just assuming things, and we can assume anything. We can assume anything we want. Is that a conditional proof shows us something about the structure of what's going on. It doesn't give us really anything concrete directly, but we're going to assume something, and we're going to see what follows from it. And then the only thing that the conditional proof will tell us is that if something were the case, then this would come from it. We can't just assume S and say, well, look, Q. We don't have a Q, but we have a maybe if S, then Q. So that's something to keep in mind. Uh, Look at the maybe before you start working on the homework for this section. Uh, Take a look at the first one that I worked through in the homework solutions videos, and hopefully that should give you more of a handle on how to work through a conditional proof. But this is a really powerful tool that we have here, especially in situations where the conclusion that we want to show in our argument, for example, the conclusion in this argument is if S then Q. Well, we can assume S and see if we can get to Q doing that, and then what we'll discharge if we can find Q in there somewhere, and this is an incorrect way to do it, was if S then Q, and it turns out that's going to be the conclusion we were looking for, so we're already done. All right.